You speak into the void and something answers back. You might ask your phone to set a timer for your pizza or ask your smart speaker about the weather tomorrow. It feels effortless, almost like magic, as if a tiny, helpful person lives inside the machine. To begin, we have to understand the fundamental difference between you and your computer. When you speak, you are creating sound waves, which are physical vibrations traveling through the air. These waves are messy, organic, and infinitely variable. They are analog signals, a continuous flow of information. A computer, on the other hand, lives in a world of pure logic and order. It doesn't understand vibrations or waves. It only understands electricity in two states, on or off. It thinks in a language of ones and zeros, a perfectly structured digital world. The core problem is one of translation. It's like trying to describe the color blue to someone who can only see in black and white, or explaining the feeling of music using only numbers. The computer needs a way to convert the chaotic analog reality of your voice into its own precise digital language. This is the hidden mountain that scientists and engineers had to climb. They had to build a bridge between two completely different universes, the physical world of sound and the mathematical world of computation. The story of how they did it is a journey into the heart of artificial intelligence. The process begins with a piece of hardware you use every day, a microphone. When your sound waves hit the microphone's diaphragm, it vibrates. These vibrations are converted into a continuously flowing electrical signal, an electrical copy of your voice. This electrical signal is still analog, a smooth flowing wave of voltage. The computer can't use it yet. This is where a crucial component called an analog to digital converter, or ADC, comes into play. Its job is to capture a snapshot of the electrical wave. But it doesn't just take one snapshot. The ADC samples the wave thousands of times every second. For each tiny slice of time, it measures the voltage of the signal and assigns it a numerical value. Imagine you're tracing a smooth, curved line on a piece of graph paper. You can't draw the curve itself, so instead you place thousands of tiny dots along the path of the line. If you place enough dots close enough together, they form a near-perfect digital representation of the original curve. This is exactly what the ADC does. It turns the smooth, analog wave of your voice into a long stream of numbers. Your voice has now been digitized. It has been translated into a language the computer can begin to process. But this initial translation is far from perfect. The real world is a noisy place. The microphone doesn't just pick up your voice. It picks up the hum of the air conditioner, the dog barking outside, or the echo of the room itself. The first task for the software is to clean up this messy signal. This is a process called pre-processing. The computer uses clever algorithms to identify and filter out sounds that are not part of human speech. It listens for frequencies that are typical of background noise and subtracts them from the signal. It also normalizes the volume, so it doesn't matter if you're whispering close to the mic or speaking loudly from across the room. This noise reduction is critical. Without it, the computer would be trying to find words in a sea of static. It needs to isolate the voice signal, making it as clean and clear as possible for the next stage of analysis. Think of it like a detective at a crowded party trying to listen to a single conversation. They have to mentally tune out the music, the laughter, and all the other chatter to focus only on the voices that matter. The computer does this mathematically. Once the signal is clean, the computer is ready to start deciphering what was actually said. It now has a stream of numbers representing your speech, but these numbers don't mean anything on their own. The next step is to break the long stream of sound into tiny, manageable pieces. The software chops the digital audio into very short segments, typically just 1/100th of a second long. For each of these tiny slices of sound, the computer performs a complex analysis to identify its acoustic features. It's looking for the fundamental building blocks of speech, the smallest units of sound that distinguish one word from another. These building blocks are called phonemes. In the English language, there are about 44 of them. The word cat, for example, is made up of 3 phonemes: the k sound, the ah sound, and the t sound. The computer's goal is to look at each tiny audio slice and make an educated guess about which phoneme is being spoken at that exact moment. It's like trying to identify individual Lego bricks from a blurry photo of a complete model. This is where the learning part of machine learning begins to show its power. The system has been trained on thousands upon thousands of hours of human speech, where each phoneme has been labeled by humans. From this massive library of examples, the AI learns what the digital signature of a b sound looks like compared to a p sound or an e sound. It builds a statistical model for every single phoneme in a language. So as your speech comes in, the computer analyzes each 10-millisecond chunk and compares its acoustic properties to the library of phonemes it has learned. It then assigns a probability score to each possible phoneme. It might determine that a certain sound has a 70% chance of being an F sound, a 20% chance of being a V sound, and a 10% chance of being a TH sound. It never knows for sure. It only knows what is most likely. This is a giant statistical puzzle. The computer uses a powerful algorithm, often a type of model called a hidden Markov model, to find the most likely sequence of words given the sequence of phonemes it detected. It's constantly asking itself questions based on probability. If the last phoneme was k, what's the likelihood that the next one is a? And if those two come together, what is the chance the next one is ta? Recognize speech versus recognize speech. Phonetically, these two phrases are very similar. A simple sound analysis might get them confused. So the computer doesn't just analyze sounds in isolation. It also uses a language model, which is a massive database of text that tells the system which words are likely to appear together. The language model knows that the words recognize and speech appear together far more often than rec and nice and beach do in that particular order. This statistical knowledge helps it resolve ambiguity. It calculates the probability of entire phrases, not just individual sounds. It essentially creates a tree of all possible word combinations and then finds the path through that tree that has the highest overall probability score. This process combines the acoustic model, which knows what sounds look like, with the language model, which knows how words fit together. The two models work together to make the best possible guess. It's a bit like playing hangman. You don't just guess random letters. You use your knowledge of which letters are most common and how they typically form words to make intelligent guesses. The computer is doing the same, but on a massive scale. Once the system has determined the most probable sequence of words, it has successfully transcribed your speech. It has turned your spoken sounds into written text. For a simple dictation app, the job might end here. But for a voice assistant like Siri or Alexa, this is only half the battle. The computer has the words, but it doesn't yet understand the meaning or the intent behind them. Knowing the words, "What is the weather like in London?" is different from understanding that you are asking a question that requires a specific piece of information in return. This is the final and most amazing step. This is the domain of natural language processing, or NLP. It's the part of the AI that deals with understanding the meaning, intent, and context of human language. The NLP model analyzes the transcribed text's grammar and structure. It identifies the sentence as a question by spotting the word what. It identifies the subject as the weather and the location as London. It classifies your request into a category, or an intent. In this case, the intent is get weather forecast. Other intents might be play music, set timer, or send message. By identifying this intent, the system knows exactly what kind of action it needs to take. It knows it needs to query a weather services database for the forecast in a specific city. If you had said, play Bohemian Rhapsody by Queen, the NLP would identify the intent as play music, the entity, song title as Bohemian Rhapsody, and the entity, artist, as Queen. This allows the system to trigger the correct function, in this case, opening a music app and searching for that specific track by that artist. It has now moved from recognizing words to understanding a command. All of this, from the microphone capturing your voice, to the digital conversion, the noise filtering, the phoneme analysis, the statistical word matching, and the final intent recognition, happens in the blink of an eye. What feels like a simple, magical interaction is actually a breathtakingly complex cascade of mathematical operations, all happening in the cloud on powerful servers located thousands of miles away. The truly profound insight here is that computers do not understand speech in the way that humans do. We hear sounds and connect them to concepts, memories, and emotions. Our understanding is rich with context and feeling. A computer's understanding is purely mathematical. It has no idea what weather feels like or what London is. It only knows that a specific sequence of sounds corresponds to a text string, and that text string maps to a specific command in its programming. The magic isn't consciousness or intelligence in the human sense. The magic is in the power of statistics and probability, executed at an unbelievable speed. It's a triumph of pattern recognition. It proves that a problem that seems impossibly complex and human, like understanding language, can be broken down into millions of tiny, logical, mathematical steps. And if you can execute those steps fast enough, the result feels like intelligence. So the next time you ask your phone for directions, take a moment to appreciate the incredible journey your words are taking. From a vibration in the air, to a stream of numbers, to a statistical puzzle, to a final, actionable command. This is the core principle of so much of modern technology. It's about taking the messy, analog, unpredictable world and finding a way to translate it into the structured, logical, and predictable world of mathematics. That is the real secret of how the world works today. It's not just about building things. It's about building bridges between our world and the world of the machine, one solved problem at a time.